So, good afternoon, good morning, good evening. Depends on where you are in the world. So, we are today again here for a very interesting talk that will be given by Tiago Reimann with a large experience at Siemens EDA in USA. So, as you can see, the talk will be about challenges and methods for hotspot detection and advanced process node yield ramp improvement. So, a lot of interesting points about the layout of integrated circuits. But today we are here to attend the talk by Tiago Reimann. So Tiago Reimann received the computer engineering degree, master's and PhD in microelectronics from Federal University of Rio Grande do Sul. He was a member of the winning team in the ISPD 2013 discrete gate sizing contest, and he has also an internship with IBM Research Labs in Austin, Texas. He joined Mentor Graphics in 2016, working in the physical design group. Tiago is currently a staff engineer at Siemens EDA in the Calibre IC Manufacturing Solutions engineering team, focusing on methods to improve product yield and provide faster ramp by structuring and analyzing massive amounts of data, creating predictive machine learning models, and generating actionable analysis. So thank you very much, Tiago, to accept our invitation to give this talk today in a very important topic with your view from the industry working in real problems. No? So thank you very much, and the floor is with you to start your talk.
Yeah. Thank you, Ricardo, for the kind introduction. And good morning, good afternoon, good evening, everyone. So as Ricardo mentioned, this talk is about challenges and methods for hotspot detection and advanced process node yield ramp improvement. So what we will discuss, and the goal of this presentation is to discuss some of the challenges in hotspot or defect prediction and detection, and how can we help to improve the advanced node yield ramp. So many of you may not be familiar with the issues that we'll discuss and we'll talk about, and even may not be even aware of the whole environment that that surrounds these kind of tools. And unfortunately, this field loves acronyms, so I have to apologize in advance because in this presentation I'll use many acronyms as well, and unfortunately I cannot explain each one of them. So throughout the presentation, I'll first discuss some questions and that are challenges on this field, given the nature of how things are and how large things are. Then second, I'll go over Sonar, that's our product, and I'll give some introduction. And of course, how much I can share is limited because this is intellectual property, but at least I think you can understand everything that we are trying to do. And if you understand the problems we are trying to tackle, you have an idea of what the industry is doing and what are the problems in this field. So also show some applications of what we have done for the past 2 to 3 years, and discuss also some aspects of the infrastructure that is needed to make things happen. So then I'll show a use case of our tool to do data selection. And in case we have extra time, I can also go over the second case, but I'm guessing I can only go over the first use case. So what are the challenges in hotspot detection and yield ramp improvement? So what are the hard questions that we need to answer, and we may not have answers yet? So first of all, what defects, right? What defects are we talking about? Is the defect random or systematic, right? The defect that you're seeing on silicon, is that due to the process or something that is not perfect on the process? Or is that something that is from noise and cannot be detected in a systematic way? So another question, can we know all the defects that happen in the layout? So after the silicon is done, we know there are some defects there. Can we find all of them? Is it even feasible to do that with the advanced nodes? Do we know what is not a defect? So we are looking for defects, but are we capable of seeing the whole layout, everything that was put on silicon, to find something that is a defect? And if we see everything, then we know that what is not a defect. But can we really do that? Then there's a challenge of size, right? What scale of problem we are dealing here, right? So we're looking at the whole layout for something that is advanced node. So can we look at that layout, all the layers on that product or on that test chip, uh, and see everything that is in there? Can we classify everything that is in there to see to find patterns and do correlation between patterns and do any classification for the whole layout, for the full chip layout? And then the question for maybe for the people not familiar with the size of things, if we have 1 million polygons on a given layer, can we do anything with that? And if we have 100 million polygons, is it still feasible to do something that we are doing with 1 million polygons? And if we have 10 billion polygons, can we do anything with that? Can we extract anything from the layout? Do we have tools that can actually manage this kind of size? And what if not only we have 10 billion polygons, but we have more points of interest that we want to classify for each polygon? So we're multiplying the 10 billion by maybe another 10 times, or even more, depending on the problem and depending on the layer. So then the question is that if we want to classify anything, do we have enough data to do analysis and classification? So do we have enough data to differentiate between things that we want to classify? And in the case, if you look at the numbers, then the problem is that do we have too much data? Is it possible that we have too much data and then we cannot do anything meaningful in terms of classification because we cannot separate the data in a way that it makes it not even easy, but possible to achieve some classification? So with that much data, so if we do have too much data, is it even feasible to write, for instance, 3 terabytes of data on a regular machine that is not a special cloud server that has super fast speeds, but kind of a normal grid machine, not only for us internal, but customers? And of course, this is even a bigger challenge for academia. So if we are capable of saving those 3 terabytes of data and we are writing them at 150 megabytes per second, it means that we need 5 hours just to write all that data. And I'm using here 150 megabytes per second because it's the top speed of a hard disk drive. Of course, we have solid state these days, so you can multiply that by 3. You still get more than 1 hour just to write the data. And then if you have to read that, okay, it's 2 times faster or 3 times faster, and then you can do that in 2 hours or maybe in 1 hour. But do you really want to wait 1 hour just to get access to the data? And if you're using, let's say, this 2.5 hours, and of course you need to load everything in memory, so you need at least those 3 terabytes of memory. So if you do load that in 3 terabytes, and then after 1 hour or 2 hours, you're just going to start to work, and then you're already using a 3 terabytes machine for more than 1 hour, and you have done nothing yet. So data is clearly a challenge. So let's say we can somehow handle lots of data, but then what do we do with lots of data? Can we analyze the data and find patterns and try to find a correlation between patterns and defects? is that possible to do with that volume of data? If we try exact pattern matching, then sorry, no problem. I was interrupted for a second. So if we do have that much data, can you use that data with the exact pattern matching to define correlation between patterns? With exact pattern matching, we have to define a search distance or a halo size around the point of interest. So how do we define the halo size? How far it's a good search distance that is not too far that everything is a single pattern? And if we, with that halo size that we choose, if we have the same pattern, but we have different behaviors on the silicon side, so the same pattern in one location, it's a defect, and in another location, it's not a defect. So what do? Do we increase the search distance? And then if we increase the search distance, how big our data becomes? Right? You see examples of that in the slides. So if we have the data, can we build a model that will understand the data and that will explain those relationships between patterns and defects? Can we improve that model if we know how to select the data properly? So that is also an important question, and you see some examples. How long it will take to actually create a model, and can we increment that model when we get new data from new layouts, from either new test chips or new production chips? How easy can we use that model, right? We may be able to create a perfect model that finds everything, but if it takes forever to tell you if something is a defect or not, it's not useful. And then it's a question that what we're trying to analyze, and if we have this, the ability to classify data and to give return an analysis on what the data means and how it can be used, can that be used also to improve other methods that are currently in use that also have problems with large amounts of data and data selection? So jump now to the introduction to Sonar, and I'll start. It's somewhat a timeline from the beginning. So there's a presentation. I'll go through some slides of a presentation from 3 years ago, and you can find that on the references. All the slides that I'm using here come from all the references that I'm pointing out in the end. So you can go and search, and if you have access to the SPIE digital library, you can find the actual original presentation also, because it's available in video as well, not only the paper. So I'll start with the why are we proposing to use machine learning methods for hotspot prediction? So for many years, doing the DRC check and pattern matching was enough to prevent those systematic hotspots on the fab side. So the fab will define what are your design rules, and if they find a pattern that is problematic, they will let the design side know that you should not be using that pattern and it can be avoided. But then DRC was supplemented with the photolithography side of with simulation and additional checks, that with a trained model, lithography model, and a trained etch model, you could find also those problems, those systematic hotspots, and adjust your layout to fix them. So today, with the advanced nodes, and remember, this is from 3 years ago, so it's already old, and we see more and more problems. We find many systematic hotspots that the optical model and the etch model, all the modeling, the modeling of the physics on simulations cannot predict and cannot find correctly. And of course, the complexity of the actual fabrication process is getting so high that all of those interactions cannot be modeled perfectly. And the lower is our signal to noise ratio, then the more we see those defects that actually cannot be correctly modeled by the optical model and edge model and everything that models the actual physics of the process. So this is the paper here on top. You see the paper and the publication. You can go over there and also watch the original presentation. So doing an analogy, and that is also from the same presentation, the idea in the beginning, right, and what we are trying to implement for we are implementing for the last 3 years, it's a way of thinking of hotspots or the defects or the patterns, the same way that Amazon or Netflix will think about product recommendation. So if you're on Netflix and you watch something and you like, it'll recommend other shows that you may also like because of historical data and other ways they are able to classify the shows and say that those are similar and people that like one also like the other. The same way for Amazon, you want to buy something and also say, oh, there's some products related to your search. And sometimes, the prediction is not perfect. You see some weird things, and that's the same for every model that we build. There's always something that is an outlier. So going ahead, instead of customer purchase history or ratings, going through a supervised or unsupervised model and predicting recommendations, we want to use the layout, the process, and the fab information to build a model and then predict the hotspots on a given layer or in a given layout that comes from either a test chip or actual product. So the analogy, doing the same analogy, is because if your fab hated this pattern, your fab may also hate these other 3 patterns that somehow are similar in a way that sometimes is not in a way that you can visibly see all the similarities, but in other spaces it's very similar. So in the process you may generate the same problem as the original one that your fab told you that it's not good. So you see those similar slides in many places in the presentation because this is very important, right? How we define features in our to use in our models to do prediction. So the feature is your source of information, right? So you define a feature vector. That is what is defining what you can see, right? How can you identify each pattern? So choosing the correct vectors is important. And of course, we are saying that we are trying to find problems on the manufacturing of the chip. So the feature vectors will be manufacturing centric. And of course, we have different applications that also apply early stages of the design. So we may not have all the data, and then I'll show you examples of how we do that, that we have some capabilities of handling things that are not manufacturing centric. But if there is enough information, we can always create a model. So in this case, that was the original, the first, let's say, implementation that was successful. We had more than 100 features that could be used that are based on layout, models, process, fab metrology, and the OPC recipes. And that, of course, is in the case where you're on the fab side and you do have the OPC recipes. For the design side of the product, they usually don't have access. So we use all those features to form a unique pattern fingerprint. So let's say you chose all your features, then you take the layout, you extract those features for all the points of interest in this layout, and you define a fingerprint. So even different layouts or patterns may generate the same fingerprint or very close fingerprint, and then you say it's a match. Those two patterns that you're seeing, they should have the same behavior in terms of fabrication. And then, of course, what can you do with patterns that have the same fingerprint? You have to understand, is that a good pattern, a bad pattern, or it's a pattern that you can ignore because it's not relevant to the data or to what you're trying to model. So the proposal of Sonar was exactly to use that fingerprint and build models that make more sense on the manufacturing side than just layout pattern matching. So you can see that this is just an example of how things can be, that we have an initial pattern and a very similar one with maybe the only difference being the distance between those two polygons in the center. And then you may have another pattern that doesn't look the same. The only similarity is that it has the two horizontal patterns, but everything around is different. So let's say that the initial pattern is a hotspot because with simulation or even in the real process, it's creating a bridge between those two polygons. It will be a short circuit, and then it will not work. But because the distance is just a bit larger on this other pattern, it's enough to avoid any problems and any bridging problems. So even though the pattern is almost the same, it's not the same fingerprint, or should not have the same fingerprint. But if you look from the point of view of pattern matching, and if you have some fuzziness on your pattern matching, it will classify those two as the same because you don't know anything about the optical model and the lithography process. And then this other one may have the same problem. So it is the same as the initial pattern. It is creating a bridge between those two polygons. But of course, pattern matching will never classify this pattern as the same as the initial pattern. But we want to have a feature vector that does. So that is one of the first, and maybe the first goal of Sonar, is to have a feature vector that can identify those similarities looking from a more manufacturing aware point of view. So initially, as we have up to today, we still have three forms of machine learning models being used. One is unsupervised, that we just get all the data or the data, the feature vectors for all the points of interest. And if you think, of course, here is only 2 dimensions, so it's visible and you can understand what is done. But if you take all the dimensions of that feature vector and then you find how close each instance of or each point of interest, the feature vector for each point of interest is from each other, and use that for classification. So it's basically just a clustering method that will find which points belong to the same cluster. So you can have a more strict cluster that you don't search very far to find to define the cluster, and then you have much less reduction, right? Because you're gonna have more clusters in the end. Or you can have a loose clustering that will reduce the number of clusters, but also it will define things similar that may not be so similar. So it's a choice depending on the application. But basically what you're trying to do here is just to group things together to assume some behavior. With semi-supervised, again, similar, we have the features, but now we also have data on some hotspots. So we know that some of these features are problematic, right? So they are hotspots or they are defects. So we use that information with the clustering to define, okay, those points that are very similar to these hotspots, they are also hotspots. And everything that is far away, it's not a hotspot. So and then we may have supervised models that we are also trying to predict things that we don't know, right? So remember on the previous semi-supervised, we are just assuming that things that are similar behave the same, but what if we want to classify things that we never seen before, anything similar to that? And then we can also build supervised models that will be able to do that. And of course, it depends on the applications. It depends greatly on your input feature vectors. Right? There's a lot of iterations to get models to work properly, pretty much on all applications. So in this case, you can predict, for instance, those points that are not so close to a hotspot, but because you can define boundaries on the feature vector space that tells you, beyond this point, it'll uh, it'll behave as a hotspot, so it's predicted as a hotspot, even if it's not close to anything you have seen before. So going back to the design side, right? So the IC designers may not have access to all the data on the manufacturing side, but we still can help them with the hotspots. So what information they have and what can be done with that information they have. So from design patterns, or let's assume that they only have design information, they don't have any information about manufacturing, we can have we can use that and maybe generate better synthetic patterns for testing. Also define partial feature vectors and do layout comparison between different layouts to find what is different, what's new between one or the other. And this is also published on this paper. We can use if they have design patterns and some process model, they can use full feature vector, right, all that I described as before, and actually do matching, reduction, and layout comparison, but with all the features. So it's going to be a better model. If they know also the hotspots, they can have a supervised model. And this is another publication. So just like I mentioned before, you can do more prediction if you have the hotspot information. And if they have everything that is possible, right, also the design, the process models, and all the information, then they can create much better model and then can predict more hotspots. So here are just some quotes from designers that the challenge is somewhat the same on both sides. They want to prevent hotspots or patterns that are problematic from being used, but of course, not all the data is available from both sides, even if they are inside the same company. That we have customers that have both sides of the product, and still inside the company, it's hard to have this sharing of data because they are either too busy or they don't understand why they need things like that. So things don't work well, even if manufacturing and design are inside the same company. So here are just some figures, and this is old, right? So it's not the way things are done, or it's possible to be done today, but just the kind of reduction you can have when you're comparing a new layout that you have with a previous one that you know things about. So you can use Sonar to actually reduce your data size, so you know where you have patterns that you have never seen before. So you can do many orders of magnitude, but of course, in this case, the difference, between each step, it's very large because this is a very regular layout. So it has lots of memory, for instance, that is all repetition. So it's easier to reduce the data. But basically what you can do from today is you take your layout and you collect your data and you compare to the data in the layout one, you can figure out exactly where you have new data based on your feature vectors, based on how you have used Sonar before. So here just a small example, and again, this is from the original slides. So the original presentation, sorry, from 2 years ago. So this is just a way of how having more hotspot data can get you to can allow you to get a much better model to predict much better. So with very small number, like a single hotspot, you cannot predict very well So you're able to predict correctly 31%, and then you get 13% of false alarms, meaning that those are not hotspots, but we think they are. If you have more hotspot data, you can get a much better hit rate depending on your clustering. So you can also see here that if you have a strict or loose clustering, it also changes a lot your results, and you can get a much better hit rate, even though sometimes you have to sacrifice false alarm because it's important to find one. So each use case is different. May prefer one or other metric to see what is a good result. So here, just a high-level view of what how the hotspot prediction works and how on which steps we are using it, or we are using that a while ago. So from your original layout with all the optical side checked and all the models used, you define care regions. That goes to the bright field inspection. That is already, you have to select regions from here to do bright field inspection. Then from those results, you have to also down select again order of magnitude to select what is going to be done with the microscope inspection. So you get to a number that is around 1,000 locations that you can do a SEM inspection. So you can use Sonar to do this down selection to tell which things are similar. So you don't have to look at those things twice. You just look one of them, and then you have you can get to your 1,000 locations coming from tens of millions. So yeah, this is again back in the day. So the goal is to classify using similar features as used in machine learning OPC. So from the product layout, you extract the features that are based on the layout, the shapes, the process, metrology, data that you may have from the fab, etc. You build a model, and then you can do a hotspot ranking and see what is a defect for sure, and things that are similar, and things that are not defects. So here's just another example, a real case example, that we initially know 44 defects. A model is created, and it only has 49% hit rate. But after that, with more known defects, you can build a better model and then have a much better hit rate. So you can check this paper also, and you can see that we are able to predict a very large number of defects compared to the original one. So coming now to what we have today and what is the infrastructure behind this. And if you think, if you can remember all the questions in the beginning, large amount of data, it's a problem, right? So one of the steps you see here, it's that we have to have database that is able to handle this kind of data. So we do have design, all these steps. So we do have design information that is either from test chips or products. We do have information from process, that it can also be interaction between multiple layers, what is even a harder problem, or from the optical or etch model, and also other process related problems that could be caused by CMP, and also stress in places where you have trenches and things like that. So we use Sonar feature vector capture, and also another technology that we have that is to be able to get some of those features much more efficiently, and build a model that is either unsupervised, semi-supervised, or supervised. And with that model and the database, we can do the analytics. So we can do pattern reduction, like the problems that I mentioned before. You have to down select pattern coverage. Also, if you want to increase the coverage with less patterns, you can check model coverage if you want to select the data that's going to be used for training optical model and other models. Layout comparison to see why a new product it's not doing as good. It's not the yield is not as good as the previous one or the test chip. You can predict hotspots, so you can take action, and depending on which stage you are, to change the layout or to change your OPC. And then you can also classify the defects to maybe understand why they are where they are coming from, and maybe solve that on the process side as well, or on your design side. And that can you can have a feedback loop and improve your model, and then get better and better on the analytics side. So back again to feature engineering, we have many sources of features. And of course, this is very critical, because the way you choose your features is defines what you can classify or not. So if you don't have enough information about a pattern, you won't be able to tell if it's different than another pattern. So we do have many ways of getting features. They may come from the design level, from measurement, and also from the simulation side, and from the pattern level. So here's some details about what your features can be as of today. So you may have features that are characteristics of the geometries. So those are measurements, and the user can define also those measurements. It's not only the features that we define upfront. Those can be also for multiple layers, right? The interaction between multiple layers may be important depending on the kind of problem you're working on. Density features, right, that tell how is the density of the layout in those around the point of interest. You can also you may also need the directional information. So if something is positioned on the top side, it's different than something being here on the bottom side. So you need to be able to differentiate those two, the density on those two. So you can also use directional kernels, and also long-range density kernels that go up to 1 millimeter. That if you have some interaction that is long distance because of your process. Then again, the litho side, that is the original feature vector, how most of the features originally were litho and process related. So those are still intellectual property, but they are all related to simulation and not information you can extract when you have an optical model and you are able to do simulation with that optical model. And you can also use features from other tools. So from OPC Verify, can also make measurements based on simulation, and you can use those features. The user can define any feature if they can extract that from the layout. You may have PNG maps, that is basically like the long range density. The customer may have those maps already, and they can be reused for feature vector extraction. And also statistics about the layout, and like area and spacing. All those features can be used, and of course it's important for depending on the application. So here just an example, or what I mentioned before in the beginning, how big your halo has to be if you're doing pattern matching. So here you can see the exact same pattern. In the left side, it's not a defect. On the right side, it's a defect. And this is using 4 times the pitch for the halo. So you can see that it's going to be the amount of data in this column. In this case, there is 700,000 different patterns you can find in this example with this size of halo, but it cannot differentiate between those two, so it will make a wrong classification. If you increase the halo, then let's say you double the halo, then you get 4.6 million patterns, and you still are not able to classify things correctly, because the same pattern has different behaviors on different location where it appears. Just because the surrounding, right, it's different. In this case, you don't have a line here that is present here. So pattern matching usually will not give you a good classification for this kind of problem, even if you increase the pitch, and then you may end up with so much data that you cannot classify anything. So from the same paper, this is just a comparison. If you use Sonar clustering to do pattern selection, just some examples of capabilities, right? That you can find 37 million clusters in a 300 million data set in 1 hour and a half using 47 features. You can use that clustering model to run prediction on 300 million locations within less than half an hour with 64 cores. And in general, for prediction, if you increase the number of cores, your runtime will reduce proportionally up to a point. And you can always, for Sonar model, you can always extend with the new data. So if you have new hotspots, you can also add them to your model, and the old predictions will be exactly the same. And here's just some examples that some clustering methods that are available uh, uh, in Python side, for instance, they cannot even run with 17 million points. So there's a comparison between how many points you can get or how many samples you can get with Sonar and those other clusters to see if they are different. So the higher this line goes, the better. And of course, random is not good, but if you do clustering and then you select a representative, it'll give you a more diverse selection if you use clustering methods. And Sonar, as shown in this work, is superior to available methods. And of course, it can handle much more data than those. Aquí again, just showing how the differences between supervised and unsupervised. As mentioned before, you don't need any hotspot data to create a Sonar clustering model. If you do have hotspot data, you can add that to the clustering, and then you can also visualize that on the tool. We have GUI for visualization. If you have all your data labeled as hotspot or not hotspot, you can build a supervised model and use that, and also improve your supervised model later. So again, back to the point of data handling, large data handling, we have some comparison of size. For instance, in many machine learning tools, the input is used, the format of the input is as a CSV or SQL. What we can generate from the layout, it has a high compression rate, and it's lossless, right? We are not losing any information, we're just compressing that based on repetition, and we can get very good compression compared to those methods that are usually used in other applications. And we can also query this data. So after we build the database interface from the data collected, you can do queries on this data, and the queries can be very fast, even for very large amounts of data. You can see here billions. I have 17 billions. You can query for locations. You can give a bounding box and find everything that is inside the bounding box in 60 seconds with a 17 billion points search space. You can also visualize what you have on your cluster, so in your clustering model. So you can also map that back to the layout if you want. We have tools for that. So you can go back in your layout. If you find a cluster that is interesting, or one that you know it's a hotspot on your Sonar tree, you can go back and see where it happens on your layout. We also have Shapley analysis that is based on Shapley value. For people not familiar, you can go to Wikipedia, just check Shapley value. It's based on game theory, and it's basically a way of understanding what your model is predicting based on the input features. So it can tell you which features are more important or less important, and you can see some distributions, because in this case we don't have linear correlation between inputs and outputs. You see that red and white is all over the place, and if you know about Shapley, and if you don't, basically you can say that the feature value goes from low to high, and then what is the contribution of that in the output of the model. So if you don't see blue and white grouped together in a gradient way. It means basically there's no linear relationship. So Shapley is still able to tell you how important things are, even if those relationships are not linear. Another application is using Sonar to help select data for training a MLOPC model. So we are not using Sonar to predict something, but just using clustering to help another tool to achieve better results. And then you can see here on the distributions that using Sonar, and I think that percentage tells how strict or not strict the model is. You can have way less prediction error than using random sampling or other loose clustering with Sonar. So it helps you to achieve a better machine learning OPC model. Again, on the data and what we can do with that is what I mentioned before about doing queries. So, and it's low latency. So we have with the MLDB, we can find all this data and all the information, can query the database to do analysis on the results, and it's able to handle very large amounts of data that you remember, as I mentioned in the beginning, the questions. It's something that was quite important, because if you have a large amount of data and you cannot search anything inside of that, it's meaningless. And of course, you can have that data not only from results of Sonar, but directly on feature vectors or with pattern matching as well. So we have a way of also doing pattern matching to generate this database based on exact pattern matching. And again, another example how queries can be fast. Even if you increase the search distance, you are still able to finish very large search distances with lots of input data. So in this case, 2.2 billion. You can still search, do a location query that has a halo of 100 microns and get all the features, all the points of interest inside that area. And this can be important for analysis when you want to see what's the surrounding of the region, and many applications can use location queries to understand what is wrong about those patterns and what are the issues that can be tackled in other ways. And in this case, with the customer case, we had 66 times compression compared to CSV. And they're also using lots of customer-defined features, and eventually the size of that of the file that was captured with feature collection of 16 gigabytes, and they can do further analysis on MLDB with that file. Again, going back to comparing chips, or the example of comparing chips, if you have a test chip, you can run Sonar on it, find all the clusterings, all the clustering, and then when you run your production chip through the same Sonar model, you can see that you have new clusters, and then those new clusters will be the new patterns, and you can visualize that and use that to improve your pattern coverage and improve your method. As I mentioned before, there's also problems that require multiple layers, because the problem itself is a result of interaction between multiple layers. So Sonar is also capable of doing that. So you can build model based on also the information you get the fab has. And we have also success stories for this kind of application, that you do a prediction using the supervised train model, and you'll be able to predict other locations that suffer the same problems. Same again, another success story with customers about improving the hit rate of prediction. So in some cases, improving very large amount just by going through Sonar and finding a good supervised model and then using that on prediction, and then getting a much better prediction accuracy. Yet another example if we have, sometimes we want to find the root cause of a defect, and so Sonar can also be leveraged to look for root cause of what is actually causing the defect, and then you can improve. You can use a non-supervised model or clustering and do analysis on that clustering, and based on your feature ranking from the Shapley analysis, you can define that, because the feature will help you explain what type or group of defects that cluster belongs to. It can also work well with Curvilinear. So if you have Curvilinear layout, it will do much better classification than pattern matching. So this is yet another publication on SPIE this year, or showing how Sonar clustering can do better classification of patterns in curvilinear designs compared to pattern matching. That usually pattern matching, you classify almost everything as unique because of curvature. The curvature changes, so everything looks different for pattern matching. And here just another example of how performance is important. In that case that I mentioned before, that the user had a feature vector with more than 40 properties that are defined by them. So the features are mostly defined by the customer. Those properties have to be, those features have to be computed, and it's quite expensive if you do that the way it's done on the layout at the cell level. So we had an improvement to have what's called SVRF block to improve the scalability of that computation, so it can be done more local and not at the global level. So you can see that in this case, it was using 1.2 terabytes of memory, and we are able to reduce that to 300 gigabytes. And with this, you can see the scale of the problems right there, using 1.2 terabytes on one machine, on the server machine. And runtime also decreased 3 times. So here's the use case that I mentioned in the beginning. That will be my last, the last part of presentation. This is a paper published last year at SPIE as well. And the goal of this paper is to find a way of selecting the data to do the training on different models, not Sonar model, to help with hard to classify patterns. So for the lithography, again, I'll jump over this because they're just trying to find where the issues are. So if you have a pinch in this case instead of bridge, or a bridge here on the right that is a short, we want to be able to find those problems and classify them correctly. So it's the same process. You define your data, you train your model, and then you want to predict that, and you want to see how good is your prediction for a different layout. One of the biggest problems is that what you know about hotspots is way less than non-hotspots. So you don't know many hotspots. And there are many patterns that are very hard to classify because they look very similar to each other, but one is a hotspot and another one is not. So the first solution that is proposed is to do a downsampling of all this non-hotspot data to reduce the data imbalance between hotspot and non-hotspot, and also do feature engineering to be able to find which ones of the non-hotspots are very similar to hotspots. So we can also include them on the data set and make sure that we are not excluding them from model training. So the same thing, feature engineering is critical. In this case, they are using, it says just saying that it's more than 100 features, not specific which features are being used. You can maybe check on the paper. Then 4 approaches are used. One is just with random sampling. That is what you do at first when you don't have much information. Approach 2 is with random sampling plus the hard to classify patterns and the hotspots that are far from the non-hotspots that are far from hotspots. And then doing the clustering of non-hotspots to down select the non-hotspots. And also approach 4 includes the hard to classify patterns. So back to that same image of clustering, If you just do random selection, you don't know if you're selecting all the clusters, and you don't know if you're selecting the hard to classify patterns that are very close to the hotspots. But you can then also add what is the ones that are close to hotspots and the ones that are very far from hotspots, and that is approach 2. But still, you may have missing clusters that are not represented on your data selection. Doing with clusters, then you select one representative of each cluster, and for those that are non-hotspots, so you make sure that you're selecting all non-hotspots, at least one from each cluster, and your data is representative of the whole set. And if you also do add one, you can also use clustering to find the ones that are hard to classify and include them on the data set for training. So how hard to classify the pattern is defined is just the Euclidean distance on the feature vector space between hotspots. Sorry, I have apparently something turned off here. So you can create a distribution based on this Euclidean distance. So with that distribution, you can see that the ones that are closer, that have a small distance to hotspots, those will be the ones that will be hard to classify. And you can select those ones, and also select the ones that are that have a large distance with hotspots, because you don't want to select everything on this big part of distribution. Otherwise, your data is not representative. So you need the both extremes to be represented to be able to train a good model. And if you do random sampling, usually you get everything here in the middle, not the extremes. So here's just how the trained model improved. And you can see that from precision of 40%, it went up to 77%. And the accuracy, it's almost the same. So accuracy here is the same as hit rate. And so you can see that on the table here how each number is computed. And basically F1 score is the harmonic mean of those two. So you want to have the largest possible F1 score. And you can see how clustering and using Sonar to select the data set improved a lot your F1 score. So that's it. So here are the references and all the papers from which I used the presentations. So thanks to everyone that helped with the slides and provided me the slides to build this presentation. You can find all those publications on SPIE Digital Library, as well with not only the paper, but also the presentation. So thank you, and you can go over the questions.
Thank you, Tiago. You told that you had another example, another case.
Do you think we have time? Or
Yeah, it's very interesting. So
okay, yeah, so I can go over the next example that is also a paper published this year, and it's a very different use case that you're not using Sonar to predict the outcome. So just like the previous example that you're using Sonar to improve a different tool, here you're also using Sonar to improve or to have better runtime in this case than another tool. So I will not go over all the details of PIX OPC, that is the inverse lithography solution that we have, but basically if anyone is familiar with inverse lithography, the main problem is that it's very slow, right? It needs lots of processing, so it cannot be applied so easily. But it's a trend on the field that it's being used more and more. So improving inverse lithography solution, it's very important for future and future nodes. So the goal, of course, is to improve a flow that is ILT guided, using clustering method to do and that guarantees consistency, and it's faster than using the inverse lithography solution alone. So here's just a description of what this PixOpC solution can do. I'll not go over the details, but you have here a good visualization of how that works. Is that if you provide in the first iteration where you have the layout, it will compute gradients and see what needs to be moved. And then each of those iterations is usually very expensive, but eventually your goal is to have almost zero gradient everywhere. So here is the result after 20 iterations. And you can see the mask here, right? The red line. It's very different from the, not very different, but it's quite different from the initial target layout. So you can see that inverse lithography is generating a new layer that is also curvilinear, right? It's not a Manhattan layer. And with that layer is what you're that layer is what you're going to use to fabricate your chip. So it's just another form of OPC, right? Trying to find a layer that actually prints what was the intended target. But as I say, this is a very compute intensive problem, even more than OPC, that is already something quite slow compared to other tools, because it needs the accuracy, right? It's not that slow because it's not efficient. It's very efficient actually, but we are pushing the limits all the time. So in this case, the idea is to use OPC, to use Sonar to help the PixOpC tool to find a solution faster. So in this case, Sonar clustering is done on the initial layout, and based on the representatives of each cluster, another tool is used to generate the sub-resolution assist features, and combining that with other tools, we get the initial mask for PixOpC. So PixOpC doesn't start from zero; it will start already from an intermediate solution. So yeah, here's what I was describing. You're combining some tools with Sonar clustering, and with that you can achieve initial mask, and then you run PixOpC with fewer iterations. So I believe the number is not reported here, but it was 60 in the example used, was 60% faster than running inverse lithography directly. So this is one interesting example that what I mentioned in the beginning. Sometimes you have actually more points of interest than polygons because you have many points of interest for each polygon. And that is usually the case when you're doing anything related to OPC, because the idea of OPC is to move fragments of those edges. And of course, each fragment then becomes a point of interest. And you want to be able to classify those fragments correctly. So in this case, it's using that solution that you're going to have many points of interest in one single polygon on your target layer. So you need to compute the feature vectors many times, depending on the location along the edge of this polygon. And then you do the classification for each one of those points. And so in this case, it was using this fragment-based point of interest. So here it's just comparing some results with fuzzier clustering. So you can see that what is predicted here is not so close to what inverse lithography it's giving as a result. But then with more strict clustering, you can see that it follows the CFCC, that is the proposed solution, can get much closer to the edge of inverse lithography. And that is the goal, right? We want to get fast and as close as possible to ILT, so ILT can have less iterations. So here's just what is input. Remember that we are using the input from the clustering based from the layout, and then adding the sub-resolution assist features, SRAFs, around not using PixelC, but using a regular tool that is rule-based and therefore much faster. So with this layout, then we do some IoT iterations, and based on that results, you can do some comparison between actually just doing only IoT solution and doing and the result with CC, and they are close enough. It's not going to be perfectly close, that is understood, but they are very close. And as I mentioned, runtime was actually 60% faster. So this is so this is the result, just the result from after running the IoT solution on the modified inputs that were created using Sonar clustering. And you can see this is a very smooth IoT solution. So here is just a summary of how Sonar was used in this test case. And I think one of the things that I'm stressing during this presentation that's very important, it's having full chip capabilities. Right? It's not, we are leveraging Calibre for that, and it's not easy to get this kind of large runs in some in a runtime that is acceptable. So it could be, depending on the solution, if you have days and days of processing, though that is usually not something that is feasible for customer. They need those runs to finish, full chip runs to finish within 12 hours, let's say the most, depending on the size and the complexity of what you're doing. So you probably noticed that I've mentioned many times how runtime and handling this kind of large layouts is important, because we are operating at the advanced nodes, so everything is large. You cannot escape from that. So that was just the extra example. We can go over the questions, I think.
So thank you very much, Tiago, for this very, very interesting talk. So I have a question here by Giancarlo Abish, but before that, if someone else has any question, please do it as soon as possible using this chat channel. So the question by Giancarlo is, can you talk about how expensive it was to train the machine learning data set in terms of data set size, computing power requirement, and the time until achieve efficient results?
So for training, ideally, you don't want to train with a huge amount of data. You want to select the data or have smaller clips of the data to do your training. So it's still, if it's possible to be done, somebody eventually will do, and that's what happens with us as well. We have customers that want to use inputs from data collected that even after compression will be 100 or 200 or even more gigabytes of data, compressed data. So it is possible, of course. It'll make it much slower, but in general, bottleneck in those cases with large data is still storage speed. So it's not impossible. You need also lots of memory right in your machine to be able to keep all this data in memory. So it is, but in general, you want to train with, let's say, tens of millions of points or hundreds the most, because that should be enough to represent everything that is possible. So it is, again, so it could be hours training a model. And remember, I cannot say details about the models, but they are not exactly the same models that you find in machine learning libraries. So they are different. So each model can have very different behavior. But for Sonar clustering, for instance, you don't need that much data. You don't need billions of points to train a model. With tens of millions should be more than enough. And that is okay to handle with in a machine that has 2 or 3 times that much memory, or 5 times. And it's handled in a couple of hours. if it's large enough. If it's small, then it's going to be minutes, and it's not a big problem.
Okay, thank you, Tiago. So another question. So you can detect a lot of defects using the method and the tool. And after detecting all these defects and so on, how normally is the procedure to correct all of them?
It depends on the application, right? So as I mentioned before, if you're still on the design side, the idea is to avoid those patterns, right? You're just trying to avoid as many patterns as you can before sending for tape out, because you can send for tape out and then they say, okay, we have all those hotspots, do something about it, because it cannot be handled just by OPC. It cannot be solved just by OPC and the tools we have internally, the fab has internally. So it depends. In that case, it's mostly avoiding and maybe making changes on the layout directly. If it's only on the fab side, so the fab is trying to find a solution for those hotspots, it could be on the process, although this is rare for Sonar applications. We have other tool that is called AIRS that is more process oriented. So it'll try to tell you what in the process is not can be improved to reduce your the number of defects. But if it's only on the OPC side, on the layer side, then it will be try to improve OPC recipe, maybe generating the OPC models, focusing more on those new patterns that are not there before. So the OPC model will be better and cover those issues, and then it's solved. It depends a lot on the application. And I am not so exposed to the details of applications, but in general, it's like that. It depends who is using, and you're trying to improve to reduce your number of defects overall. So any step you can do, change the layout, change OPC recipe, anything that is it's available for you as a tool to modify and reduce your hotspots, then the user will go and make those changes to improve the results.
Yeah, also all these input, these results can also be used to change or improve some synthesis tools, no?
It depends again where you are. Yes, it could be used as when you know the patterns. I am not sure how people do that today, but for sure it could be used as to provide inputs for the higher level on the physical design side, to avoid those patterns to begin with and not have to correct them after DRC. But in general, what we are talking is it's already after DRC, right? Everything is already done.
Yeah.
It's passing all the design rule checks, but still the fab tells you, I don't like that pattern, so do something.
Yeah. Okay, so thank you very much, Tiago. I see no more questions here in the chat. So it was a great talk, and so people are aware that when we finish our layout, is not yet finished the whole
Oh,
history.
it's not even close. Yeah.
Yeah. So thank you very much.